Okay, here we go. So for today, we're gonna plug in something new. This is a good shortcut. So we're gonna look at think what we've done here so far in Unit 4. And I know it's been kind of we've missed days and it's been kind of hit and miss when we've been in here. But so think about what we've done. We've talked about factoring, right? And we've talked about how we can use factoring to solve equations that are factorable, right? To solve quadratic equations. And then we kind of took a little break and we looked at some conversion stuff, converting between the different forms of quadratic functions. And you'll see why we did that here shortly. But now we're going to kind of jump back on the solving equations train, right? So we're going to look at another type of a quadratic equation, but this is a different kind. So make sure once you click all those Chromebooks closed and get everybody's undivided attention up here, please. So this is a kind where that doesn't look like a trinomial, does it? Right? It doesn't look like ax squared plus bx plus c equals 0. We could put it into that form, right? How could we put this into the form? How could we put this into the form ax squared plus bx plus c equals 0, which is that's a quadratic equation in standard form, right? How could I go about that? Okay, good. I could expand out 3x minus 4 squared, and then I could combine like terms and subtract 76 from both sides. I could do it, right? I could do it using algebra, okay? But if I did that, and I could get an answer that way, presumably. I could put it into that form and then maybe try to solve by factoring or use some other technique. But I don't want to, because it turns out that this is a really good opportunity for me to get an answer very easily when it's in this form. And here's the key. How many different variables do you see in that equation? You only see one instance of an x, don't you? Right? So that's different than the other quadratic equations we were solving, where we had x squared terms and x terms, right? Those required us to do something tricky like factoring. But in this case, because I can point to a single variable, I can isolate it, right? I can just reverse my order of operations and isolate the variable. And we'll go into more detail about how we do that soon. The process of doing that, though, if we look forward, if I think about the steps I'd have to do to get that x by itself, what would I have to do to get the x by itself? And if we think back to how we solved linear equations, even fairly complicated linear equations, which now would seem very, very simple, how did we do that? How did we use the order of operations tree? To isolate a variable or something. Bottom to the top. We used inverse operations, right? So to get the variable by itself, first we had to undo addition or subtraction by subtracting or adding, right? And then we undo multiplication and division by dividing or multiplying. Then we undo exponents, and finally we get up to parentheses. We undo anything in parentheses, right? So can you I'm not even going to write anything down here, but let's see if we can talk through what are the steps we'd have to do then to get that x by itself. What would the first step be? I'm going to add 5, because outside of parentheses, the only addition or subtraction I have to undo is adding that 5. Agreed? Okay. Then what? Okay, yeah. Now there's no multiplication outside of parentheses to undo here, is there? But I have to somehow undo squaring this quantity to get at that x, don't I? Right? So how do I undo squaring? I got a square root. Okay, so you can already anticipate that we're going to have to deal with some square roots, right? With square rooting things, and that's going to involve simplifying some radicals, simplifying some square roots. So does it make sense then that we want to backtrack a little bit before we jump into this new technique? And it's not hard, but before we jump into this, maybe we want to take a second and just review how we deal with radicals, right? So let's do that. Let's start off by the process of simplifying radicals involves prime factorization. So let's kind of go back to, I don't know, when did you guys first talk about this? Probably, I know you did in Algebra 1, probably talked about it a bunch. But you would have even maybe been before that, probably, I think possibly. How did you guys go about factoring a big number like that, 2520?
For an even number, I'd just divide it by 2.
Okay, so you could, but how did you represent that? Because there's a bunch of ways you could. We could write this out linearly, but there was a nice little, a tree, good. So you remember factor trees, right? So we'll start with the number 25, 20, and we're just gonna break that apart into factors until none of the branches can be broken apart, can be split any further, right? Now, there's a couple things, and there's no one way to do this. We know that it's even, so we could just divide, we could factor a 2 out, right? Divide everything by 2. It's convenient, though. It's convenient if you can. It's convenient to try to break off a little bit bigger number so the tree doesn't get so long. So what about, okay, we can do 10 or even 20, couldn't we? We know that 20 is going to go into 1,000 evenly, right? So it's going to go into 2,000. It's going to go into 100 evenly. So it's going to go into 2,500 evenly, right?
Yeah.
And it goes into 20. So does everybody agree that we could divide 20 into that? It'd go evenly? Okay. Do you have to use that big one? No, we could have used 10. But if we can use a slightly bigger number, it just makes this a little less cumbersome. So we're going to split this up into a 20. And what else? Let's just do 10. 10's so easy. We'll just do 10. 10, and then we get 252, right?
Yeah.
Okay, what about 252?
126 and 2.
126 and 2. Okay, so we can do that. We can go 2 and 126. 126 we break up into 2 and 63. Okay. 63 we break up into, okay, but we could maybe even do like 7 and 9. Okay, so we could do 7 and 9, and then 9 breaks up into 3. Okay, what about the other branch up here at the beginning? 10 breaks up into 5. Okay, so now we got it's factored down to primes, isn't it? Everything at the end here is a number that can't be factored any further, right? So then how would we say this? 2,520 written in prime factored form would involve what prime factors, first of all? 5, 7, 2, and 3, okay? But I've got a bunch of 2's there, so how would I represent that? 2 to the 1, 2, 3, it looks like, right? So I get 2 cubed times 3 squared times 5 times 7. Okay, make sense? Okay. Now, you remember doing that stuff? Yes, ma'am.
Do you want us to do it in, with the exponents from highest to lowest?
Well, normally what you would do is you'd write the prime factors from the smallest to the biggest.
Okay.
So we do the 2's first, then the 3's, then the 5's, etc. Okay, so then, next issue then, right? So we know what we mean by prime factorization. Now, what if we want to simplify a radical, simplify a square root? So without getting into too much detail, can you just, you have to be very mathematical about this, but just conceptually speaking, what does it mean to simplify a radical? What am I trying to do? Smallest number possible where? In the radical, good. So we want to get as much out of the radical as possible, right? And leave in as little as possible. And if it turns out that the number, if this is a perfect square, like 100, we get everything out of the radical, right? The square root of 100 is just 10, right? And that would be our answer. But if we had something like the square root of, 18 or something, 18 is not a perfect square. So we're going to get stuck with something under the radical in that case. We just want to minimize that, right?
And if it's like 7, then just leave 7 in.
Right, exactly. Okay, so do you remember learning about couples go out, singles stay in?
Yeah.
Okay, you do. Okay, so maybe, yeah, we'll talk about it, yeah.
So
all we got to do then, if we want to simplify this radical, let's take a simple example for a moment. Let's take the example, what if we had like the square root of 18? Take a really simple one. The square root of 18, what's that going to simplify into?
3 and 6.
3, okay, 18 breaks into 3 and 6, and 6 breaks up into 3 and 2. Okay.
So 3 on the outside and then.
Okay, 3 on the outside and 2 on the inside. There's another way to look at that, and that is I could say this is a property of radicals. I know that in general the square root of a times b is equal to the square root of a times square root of b, right? That make sense? That makes sense to everybody, that would be the case? It is. So then 18, I could break this up into the square root of 9 times 2, right? How come I pick 9? Okay, what do we call that kind of number? Perfect square, right? So 9 is a perfect square factor of 18. And so then when I break this up into separate radicals, I get the square root of 9 times the square root of 2. And what's the square root of 9? 3. Okay, everybody get that? So that's our goal. All right, we want to get the biggest thing outside that we can. Okay, so with very big numbers like this, with 18, the easiest way to do it is just think to ourselves, okay, what's the biggest perfect square factor of 18? Right, we can do that. We can manage that pretty easily. But nobody's going to be able to tell me what the biggest perfect square factor of 4410 is. Right, that's a pretty big number. Right. So what we do instead is we're just going to set up a factor tree for 4410. So it ends in a 0, so why not pull out a 10, right? So we get 10 times 441. What's a number that divides evenly into 441? 3 does. How do you know? But there's a way you can look at that number and tell them. It adds up to a multiple of 3, doesn't it? It adds up to 9, which is a multiple of 3. Okay. So then we can take out a 3, and what are we left with? Well, 3 goes into 4, 1 with 1 left over, goes into 14, 4 times with 2 left over, so 147. Okay? What's a number that divides into 147? Well, no. 3 does, right? Because 1 plus 4 plus 7 is 12, which is divisible by 3, right? So we get 3 and 49, right? So 7 does, I guess, yeah, actually. And then 49 breaks up into 7 and 7, right? Okay. What does 10 break up into? 2 and 5. Okay, so now look, we got this thing factored, so we have prime factors only, right? Factors, the only prime factors of 4410. So now all we have to do is we have to think about, if I took 4410 and I wrote this number down as a product of all these factors, right? So 4410 equals 2 times 3 squared times 5 times 7 squared, right? Everybody agree? And if I'm taking the square root of 4410, it's the square root of the product of all those things. Agree? Okay, but look, we can use our property up here. The square root of a product is equal to the product of the square roots. I can break that up into 4 separate square roots, right? I'm going to get the square root of 2 times the square root of 3 squared times the square root of 5 times the square root of 7 squared. Well, what's the square root of 3? The square root of 3 squared is 3, right? So I can pull the 3 out front. The square root of 7 squared is 7. And then I'm stuck with the square root of 2 times the square root of 5, though, aren't I? Right? So I could turn that into the square root of 2 times 5, and my eventual result is I get 21 radical 10. Okay? Right? That's a lot of work to show, though. Here's a little shortcut way of showing that. What we can do is we could put all the couples in boxes and the singles, however you decide to do it. I can't remember how I used to do it. We'll do couples in boxes and singles in circles. How about it? Maybe it'd be easier to do it the other way. Let's go, actually, let's do it the other way. I think it's easier to draw that way. So we'll go couples in circles and singles in squares, singles in boxes. Right, so then look what we get here. I've got a couple of 3s, I've got a couple of 7s, and I've got a single 5 and a single 2, right? So we know then that because I'm going to get a square root of 3 squared, that 3 is going to pop outside the radical, and the square root of 7 squared pops the 7 outside the radical. Just remember this little saying, couples go out and singles stay in, right? And so when we simplify the square root of 4,410, we're going to have two parts to our answer. We're going to have an outside part, and we're going to have an inside part. Any factor that shows up as a square, so it shows up in a couple, is going to go outside, right? Is this ringing a bell? So we have a couple of 3's, so I know I'm going to get a 3 outside. Couples go out. I get a couple of 7's, so I get a 7 out, and then I get a single 2 and a single 5. So those stay in, right? And that gives us our simplified answer of 21 times the square root of 10. Everybody see that? You want to try one of those real quick for practice? No. You don't? I mean, would you like to? You think you got it? Okay. Think you got it? Okay. So we're good. So there's the trick. Couples go out, singles stay in. Let's look at some stuff like this then, right? I don't know if maybe you didn't do something like this. Now, what are our options here? If I've got the square root of 2 times the square root of 10 times the square root of 15. Okay, I could do the square root of some big number, right? That's going to give me, what, the square root of 300? Okay, I could do that. I could just turn this into the square root of 300 and then proceed as we just did in the last example. That's fine. Okay, do I have to, though? No, not really, because I could be a little smarter about this. It's already factored some stuff for me, hasn't it? Right? Think what we've done here. What this is telling us right now is that whatever the big number is, and we don't even have to know what it is 300. But what if we didn't even know that? Big deal. We don't have to. Oh, come on, don't crash on me. Please don't crash on me. It's making your tape of this, so it's crashing on you, really. That's never a good sign when you see that little spinning wheel.
It stopped.
It stopped? Okay, good. Okay, so we've got some mystery number up here. We don't even have to know what it is. It turns out it's a 300, but isn't this just telling us that the 300 is breaking up into these factors, 2, 10, and 15, right? So even if I don't know what that is, I don't care because I know what the factors are that multiply to it, right? 2 is already prime. 10 breaks up into what? 2 and 5, and 15 breaks up into 3 and 5. So look what we got. We get a couple. Come on now. We get a couple of 5s. We get a couple of 2s. And we get a single 3, right? Oh, man, I've seen it again. I don't know why it's doing it. It never does this. Right? Take advantage of the fact that it's already factored a little bit. And so we end up with our answer being what? What goes outside?
2 times 5 is 5.
Good. 2 times 5 goes outside. And then inside we get, right, so our final answer just looks like 10. Right? See what I'm saying? Couples go out, singles stay in. We got a couple of 2s, so a 2 goes out. A couple of 5s, so a 5 goes out. See my point? Okay? All right, what about something like this? What happens if you divide square roots? Yeah, right? We can just simplify that as... Say it again? Are you wondering what happens if the bottom isn't a perfect square? No. Okay. Okay. Well, that's what we're doing next. So what about this then? I can just take the square root of the top and the square root of the bottom. It's fine. What's the square root of 36? 6. What's the square root of 16? 4. Okay, so that's equal to 3 halves. No big deal. Easy, right? Okay, but what about one like this? And I actually want to, hey, listen, I feel like I'm losing some people here. So I actually want to start this in a slightly different place. What if I gave this to you instead as, what if I gave this to you as the square root the square root of 169 over 50. If I have the square root of a quotient, I can break it into separate square roots, right? I have a similar property to what I had in the last example. The square root of a over b, so the square root of a quotient is equal to what?
The square root of a over the square root.
Good. Quotient of square roots. Okay. And so I can get it to here. Now what? Okay, that's a perfect square. 169 is what square? 13. Good. So the top works out great. On the top we get 13. What about the bottom? Okay, so we could make a factor tree out of the bottom if we want to. We could probably avoid it, right? We could probably think about what's the biggest perfect square factor of 50? We're going to get 25 and 2, right? The square root of 25 is 5. So we would just get 2, 25, 5, and 5, which is giving us a couple of 5s and a single 2. So on the bottom, we get 5 times the square root of 2. When I simplify the top and I simplify the bottom, right? Okay, what's wrong with that? Can't have a square root on the bottom. Did you guys learn there's no tents in the basement? No one? Oh.
I didn't learn that same, but I learned you can't have a square root.
Yeah, okay. Well, a lot of books say that you can't have no tents in the basement, so you can't have any radicals in the denominator, right? So what do we do about that? That's against the rules if we want to write this in standard form of a. Okay, good. So in order to get rid of the square root of 2 on the bottom, what are the things that I can do to a real number and not change it? I can multiply by 1, or I can add 0. Well, seldom do we ever add 0, sometimes. But we do this a lot. We multiply by 1 an awful lot. If I multiply by 1 in the form the square root of 2 over the square root of 2, that works, doesn't it? I multiplied by 1, same thing on the top and the bottom, but the square root of 2 times the square root of 2 is what? 2. How come? Because the square root of 2, there's two ways you can look at this. The square root of 2 times the square root of 2, sure, that's equal to the square root of 4. And what's the square root of 4? 2. Okay, yeah, that works, but here's a better way. The square root of 2 times the square root of 2, how can you write it when I multiply something by itself? What am I doing? I square it. So that's the same thing as saying the square root of 2 squared, and what does squaring a square root do? They're inverses, they cancel, right? And so I just end up getting 2, right? Yes? Yes. Okay, so what does our answer look like then?
13 squared 2 to 10.
Okay, so on the top, we're going to get 13 radical 2, right? On the bottom, I'm going to get 5 times 2, which is 10.
You're multiplying the 2 and then you square root it on this.
Okay? And then now I could ask myself, can I reduce that any further? 13 over 10 doesn't reduce, but if it did, I could reduce that fraction, right? But we're stuck, because 13 is prime, and so, 10 and 13 have no common factors. Yeah.
What if it was, like the 5 wasn't there and it was just the 2 squared?
Then it just would have been a 2 on the bottom. Okay? Make sense? Okay? All right, so then now we get up to some problems where we practiced simplifying radicals. Now let's go to work. Now let's actually use this in something that is applicable to what we're now talking about, to solving quadratic equations. And so here's the statement that I made earlier. When solving a quadratic function, I should say equation, actually, let's change that. We don't solve a function, we solve an equation. When solving a quadratic equation where you can point to a single variable, you can isolate the variable by using inverse operations, right? Reversing the order of operations tree. Okay? So what would the steps be then to get that x by itself if we follow PEMDAS? Yep. So if we just reverse order of operations, first step is going to be add or subtract, right? So we're going to subtract 44 from both sides, and that gives us 4x squared equals, what is that, 392? Okay, now what? Divide by 4, right? So next step, multiply or divide. We divide by 4. And that's going to give us x squared equals 96. Okay? No, that's 90, should be 93. 98, there we go. Okay, good. So we made it up to there. Now what? Okay, square root. Okay. So last step, I'm gonna and I undo the squared by square rooting, right? Everybody agree? Okay, so if I square root both sides, what do I get? So that's this step. Okay, you remembered. Okay. So what's the rule? If I'm ever taking any even root, but for now that only means a square root for us. If I ever take an even root of both sides of an equation, I always have to introduce a plus or minus, right? Always. So I've got to put a plus or minus out front, and then I just get the square root of 98. Okay, well, can we simplify that? Square root of 98. Let's make a little factor tree. 98 breaks up into what? It's even. So I could go 2 times 49, and 49 is a perfect square, so I get 7 and 7, right? So I'm going to get a couple of 7s and single 2, right? So I get plus or minus 7 radical 2, plus or minus, right? Everybody with me? Okay, how come we put that plus or minus there? Okay, it could be, because here's one way to think about it. Because what numbers square to 98? Well, 7 radical 2, or a negative number squared gives me a positive answer also, right? Does that seem like that's a really good proof, though? Not really. I mean, it works, but how would you know to do that algebraically? I'm going to show you the missing steps. I guarantee you've never seen it. So the missing steps. What is, and you're going to like this, though, because it relates to some stuff we've already done. So what is the square root of x squared equal to, do you think? X? No, it's not. I'll prove it to you. I'll prove it to you. The square root of x squared is not x. Because let's think of it as a function. So let's make f of x equal to, if f of x is equal to the square root of x squared, the suggestion is it's x is the answer. Well, if I plug in 7, the square root of 7 squared is 7. Seems like x, doesn't it? Because if I made, let's just compare it to g of x equals x. F of 7 equals 7, and g of 7 equals 7. Seems to work. It sounds like you're right. What's a value I could plug in that's not going to work? Negative 7. If I plug in negative 7, g of negative 7 would give me negative 7. But the square root of negative 7 squared is what? Positive 7. It's not negative 7, it's positive 7, isn't it? Well, what function does that? What function leaves positive numbers alone but makes negative numbers positive? Absolute value. There you go. So really, the definition of the square root of x squared is actually the absolute value of x. So the missing step that you never see in the textbooks here is the square root of x equals positive 7 radical 2. Because here's something that a mistake you're prone to make. What is the square root of 49? 7. It's not plus or minus 7. It's 7, isn't it? The square root of 98 is positive 7 radical 2. But look what we ended up with. We ended up with an absolute value equation. How do we solve absolute value equations? Yeah, whatever's inside is equal to the positive or it's equal to the negative, isn't it? Going back to that beginning of the year, right? So that gives us our answer, x equals plus or minus 7 radical 2, because this evolves through an absolute value step. There's an absolute value equation there. Do you write that step? No, you don't. We just know, we just remember that it's always going to work this way, and that if I take a square root of both sides of an equation, I've got to introduce a plus or minus. Okay, but that's why technically you do it. Okay. All right, so then we ended up with our answers. We got plus or minus 7 radical 2. Let's go one step harder. Let's look at something like that. Okay, so once again, I can point to a single x, can't I? Right, so this is the one we started with at the beginning. So now we're going to reverse order of operations, just like before. First step is going to be add or subtract, outside of parentheses. So I add 5 to both sides, and I get the quantity 3x minus 4 squared equals 81. Okay, what's next? Square root, because the very next thing is I've got something squared, right? So if I square root both sides, I end up with, and that's going to be, I guess, this step right here. So we're going to end up with the quantity 3x minus 4 equals what? Plus or minus 9. Everybody agree? Do I need those parentheses? No, I needed them here because I had a quantity that was being squared, but here I do not because nothing is being distributed and we're not taking it to a power. So they don't do anything anymore, so I can get rid of them. But that brings us up to the parentheses, flips the parentheses step, doesn't it? Right? We don't need them anymore, but now we're to where the parentheses were originally. What are the last 2 steps in order to isolate x? Add 4 and divide by 3, in that order, right? So when we add 4, think about how we could do this the best way. When I add 4, I could add the 4 after the plus or minus 9, so I'd get plus or minus 9 plus 4. But wouldn't it make more sense to plop that 4 down in front of the plus or minus?
Yeah.
Because then look what we get. If we add 4 to both sides, look at those answers. They're easy to calculate. 4 plus 9 is 13. 4 minus 9 is negative 5. Right? So when you get to this stage and you're solving these quadratics, it really is easier to add the number in front of the plus or minus. And then what's the last step you said? Divide by 3. Okay, so last step, we divide by 3. And look, there are both of our answers encapsulated in one statement. So then if we want to see what x is, we could take the plus sign, and the plus sign is going to give us x equals 4 plus 9, which is 13 over 3. There's one solution. If I take the minus sign, I get 4 minus 9, which is negative 5 thirds. There's my 2 answers. Okay? Make sense?
Yep.
Okay, one more. We'll call her good. One like, actually I want to do one like that one. Let's give up to that one. Okay, so what do I do here? Okay, first thing I'm going to do is subtract 9. Agreed? Because I got it outside of parentheses, I subtract 9, add or subtract, and I get negative 2 times negative 5x minus 3 squared equals negative 112. Now what? Divide by negative 2. Good. And so that's going to give me the quantity negative 5x minus 3 squared equals positive 56. Okay, now what?
Now it's
Square root. So if I square root both sides, I'm going to get negative 5x minus 3, because that cancels the squared, right? Equals plus or minus. And then let's take our 56. That breaks up into 7 times 8. 8 breaks up into 2 times 4. 4 breaks up into 2 times 2, right? So we get a couple of 2's, and we get a single 2 and a single 7. So I get plus or minus what? Okay, good, that's a 2, so I'm going to get plus or minus. Couples go out, so 2 goes out, times the square root of 14. Agreed? Okay, last 2 steps. Add 3. So I get that. Okay, and I'm going to write this step down separately, because this last one, I want to talk about this one. There's a way you can make this easy, more complicated. Okay, what am I going to divide by? Negative 5. Okay, so when I divide both sides by negative 5, what's that going to give me? Over here, I'm going to get 2 terms, aren't I? I'm going to get 3 divided by negative 5 is negative 3/5. Agreed? Okay, but what about this? Do I need to divide this by negative 5? How come? Yeah, I'm already doing plus or minus, right? I'm already taking both signs of that. So why complicate this by dividing this part? I divided this one by negative 5. I could divide that by negative 5, but it makes no sense because I'm taking both signs anyway. So why not always just divide this one by the absolute value? See my point? Don't divide by negative 5. Divide that second term that's already got the plus or minus there. Just always divide that one by the absolute value, the positive one. Then you don't have to worry about, that's confusing otherwise. I get plus or minus a negative fraction. Doesn't make any sense, right? I mean, why do that? Plus or minus a negative fraction is the same as plus or minus a positive fraction, right? So it just eliminates some confusion if you do it that way. So my final answer looks like negative 3/5 plus or minus 2 radical 14 over 5. We're done. Okay? Make sense? I get 2 answers, one for the plus and one for the minus. Okay? We good? So I got 2 assignments up to practice that. Let's say, okay, I'll tell you what, I'll make the first one, which is just kind of the fine factorizations and simplifying radicals. Let's make that one due Friday. That's the last assignment of this semester. The other one I'll push into next.
So is that 4.3?
So it's going to be 4.4 practice 1 and 4.4 practice 2.
Or, so how many are?
So only 4. I'll put it on the calendar. Only 4.1 is going to be for this semester.
So all up to 4.
Well, up to 4.1, up to 4.4 practice 1. 4.4 practice 2, I'll make you on Tuesday, so that's next semester. So that one I will collect. That one's gonna go on this semester. This semester. Yeah, everything in 4.3, well, I'm gonna put on this semester's grades. Does that make sense for you?
Sometimes something so I read too.
Nora.
Sometimes.